Thank you so much for the introduction. So I'll be presenting the paper Fast ACS. So this is the problem statement that we are trying to solve. We have a producer which is trying to generate messages, and this messages needs to be delivered to the consumers. The messaging system that we have needs to offer the following guarantees. First, messages should be delivered in exactly the order they were produced, so there should be total ordering, and every message should be delivered at least once. So this is very classic old distributed system problem, and this has already been solved by Kafka and Pulsar, and there are many other systems out there solving this problem. But what we are trying to do is trying to solve this for a very large scale. Our consumers are distributed across the globe in dozens of clusters. We have tens of thousands of consumers per cluster, totaling in about hundreds of thousands of consumers globally. And the consumer read traffic in any cell is in Tbps range. At the same time, when we are delivering messages, we are trying to achieve sub-second tail latency end-to-end. This is how a traditional ordered message delivery system looks like with Kafka. We have a producer which generates messages, and these messages are appended to something known as a message file, which is stored on the storage media. And we have a system called Broker, which stores this message files in its local storage. And we have consumers trying to read these messages. They read the bytes from the message file, and then they deserialize the message out of them. This has a limitation that it cannot scale to tens of thousands of consumers, mostly because the storage media has some limitations. For example, SATA SSDs today have limitations of 4.84 Gbps bandwidth, which cannot support tens of thousands of consumers. And we have verified this with Kafka. We ran an experiment with Kafka on Google Cloud. We had 3 brokers in a zone, 8 vCPUs, 32 GB RAM, and NVMe SSDs for each one of them. We had a producer byte rate of 240 Mbps, which was distributed across all the 3 brokers. And the results that we observed was a maximum of 56 consumers were supported, and the peak consumer byte rate was about 14 Gbps, after which both the producer and consumer throughput plummeted. Now there are 3 sets of solutions that we have implemented to get around all those limits. Solution 1 is to retain the recent messages in the memory. So we segregate the messages into 2 categories, hot and cold messages. The cold messages are meant to be stored in the storage media, whereas the hot messages that are the most recent one, which the consumers are interested in, tail reading them, they are stored in memory so that we don't access storage media. The storage media just acts as a fallback whenever the consumer wants to go back and fetch the old messages. This lets us get around the limits of storage media, but this still has another problem, the network interface card. Currently, it has some transmit limits, and terabit NICs are going to be a bit far, and they are not going to be deployed in production for a long time. So they have some limits, for example, 10 Gbps. And in order to get around the NIC limits, what we do is we take the message file, we divide it into smaller chunks. We distribute those chunks among n number of brokers, and consumers are expected to fetch those chunks from those brokers and then assemble the message file out of them and deserialize the messages and deliver it. So in this process, we have another problem that as we scale out the number of brokers, we are also paying the cost of processing. And to get around that issue, what we do is we make use of RDMA. So instead of brokers delivering the message to the consumers, we make use of RDMA, and consumers use RDMA to fetch those chunks. And this is very useful because now we are able to scale out horizontally without paying the processing cost, and we can effectively utilize the power of several NICs in a cluster. And we have put together all these 3 to build something what is known as Fast ACS, and this is a part of Google Ads infrastructure team. We have real-time extractors which generate message streams. These message streams are sharded into message stream shards, and each of this message stream shard has a message file. So messages within a message stream shard is going to be totally ordered. These files, message stream files, are tail copied from source cluster to destination cluster, and the consumers in the destination clusters are continuously tailing this file to get the messages from those files. For the storage, we make use of 2 layers of storage, L2 and L1. In L2, we have Colossus, which is a distributed file system developed at Google back in 2003. And it stores the message files in hierarchical directories, so it helps in discovery as well. We don't need an explicit broker layer for discovery of message files. The files that we have on Colossus are append only, and this is a very interesting property because once the message has been appended to a file, it can be delivered safely. All reads and writes to Colossus are RPC based. In contrast, we also have an L1 layer in which we make use of ClickMap, which is a RDMA based volatile distributed key value store. All writes to the store are via RPC, but all reads are via RDMA. And this is very interesting because most of our traffic, more than 99% of our traffic is consumer traffic, which can make use of RDMA to read the messages. ClickMap makes use of consistent hashing for distributing the keys, and it is replicated. It supports R equal to 3.2, so it is resilient against faults. And essentially, the L1 layer that we have, it minimally replicates Colossus features that is most relevant for ordered message delivery. So diving a bit deeper into the cache layer, we have two sets of job, data cache and metadata cache, and these are very analogous to their equivalents in Colossus. So data cache is equivalent to chunk servers and metadata cache is equivalent to big table. In the data cache, we hold the file chunks and we divide the file into 4 KB chunks, which is based on the maximum transmission unit in the cluster fabric. As we write new chunks, the old chunks are removed based on the least recently modified policy. Every chunk is identified by the file path and the chunk sequence number, and the file path is globally unique on Colossus. So every chunk can be identified uniquely on the data cache. In the metadata cache, the most important metadata that we store is the file length, and this is the only metadata that we really need for ordered message delivery. We also have file lock, which is the best effort entity for avoiding dual writers. Now, the core difference between this Colossus and cache layers are the cache layer is volatile, so any key value can be lost at any time, and we do not depend upon this property for correctness. Additionally, the cache layer has no server-side processing. So all the cache layer can do is write key value pairs, but we have to build a file system explicitly on top of that, and client needs to handle all the files interaction. And this is the basic flow of our system, considering there's no cross-cluster replication. So producers are responsible for writing the bytes to message file on Colossus, and then writing the corresponding chunks, shadowing the corresponding chunks to data cache as well. When these two are finished, they write the length to the metadata cache. Consumers are continuously pulling the metadata cache, detecting changes in file length, and upon detecting a change, they read the chunks from data cache. And if for some reason there's a miss, for example, the data cache is volatile, it can remove any chunks at any time. So they will fall back to CNS to fetch the corresponding bytes. And this is how things work when we are considering cross-cluster delivery. So first, we try to build a copy tree. Directly streaming all the bytes to the destination is going to be very expensive. So we build a minimum spanning tree of cluster, which is prim-based. The weights that we used is the bandwidth cost across different links. We have some other constraint as well, like the maximum depth that the tree should have, or the maximum fan out from each cluster. The message streams are routed along the copy tree, so every message stream is going to receive a unique copy tree for themselves, and typical depth of a copy tree is going to be about 4 nodes. We have 2 sets of jobs, readers and writers, along each hop. Readers are going to act like consumer. They're going to read the bytes, but instead of deserializing messages out of them, they're going to stream the bytes to the next hop. Writers read the bytes, and receive the bytes from readers, and they write the byte to the destination cluster storage. We have a unique operation pair for every file, one for cache and one for Colossus. So Colossus stream is the one which writes to Colossus, and cache stream is the one which writes to cache. Colossus stream acts as a delayed fallback stream. It is slightly delayed, whereas cache stream is optimized for latency and throughput. It supports parallel out-of-order writes, and you can find more details in the paper. This effectively doubles the bandwidth utilization, but this has been very, very useful in solving the use case of low latency for us. Apart from readers and writers, we have a scheduler job as well, which is responsible for scheduling operations on readers and writers and managing their life cycle. And scheduler's availability is very critical. Let's say some readers or writer job goes down, then scheduler is the one responsible for rescheduling it immediately so that the stream almost remains uninterrupted. But it is possible that sometimes the scheduler becomes unavailable. In those cases, we allow an operation to execute in orphaned mode And when the scheduler comes back up, it can schedule a new operation which can overtake the existing operation. So the stream remains uninterrupted. Now to implement this overtake, we make use of file lock on Colossus. So for Colossus, because there is server-side processing, so file locks are available. If a new operation comes up, the existing operation will go away. But this implementation is very complex for cache because there is no server-side processing. And in this case, we need to choose between consistency and availability, and we chose for availability. So there can be multiple cache streams active for the same message file at the same time, but this does not affect the correctness of our solution, and we deliver the bytes correctly. And you can find more details of how we do it in the paper. So once the bytes have been delivered to the destination, the consumers have a choice either to read it from the cache or from Colossus. We try to not read from Colossus as long as possible because reading from Colossus burns disk time resources. So we delay the reads from Colossus unless the message delivery is really at risk. And this has been very useful in saving us a lot of Colossus resources, disk time resources. For evaluation, we have considered the following metric. One is the delivery delay. This is measured as the time when the producer creates a message in memory and the time when the consumer has deserialized the message. So this is the end-to-end delay, and this includes everything. And we also include fallback, which is the number of reads that goes to Colossus. So whichever reads are not successful from cache, they go to Colossus, and this is something that we try to minimize as well. So in our evaluation setup, we make use of shared BOR, which has the same noise as production. We make use of high priority CPU resources. We use Pony Express, which is a software RDMA platform developed at Google. And we make use of B4 network for cross-continental traffic, which is a non-user facing network. We also have producers buffering the message for 100 milliseconds because if they write every message, the cost is going to be very high. In the first experiment, we had 2 message streams. The total write rate was 240 Mbps, and we had 15 destination cluster. Scaling was not enabled for this experiment. We had 9 data cache replicas, and consumers were pouring at 50 milliseconds, and each consumer was reading 8 Mbps worth of messages. And this is what we have from experiment 1A. We scaled up the consumers from 0 to almost 8,000. No Colossus fallback was observed. The delivery delay was 500 milliseconds. Most of the delay was from producer buffering, which was 120 milliseconds, network delay 180 milliseconds, 100 milliseconds. All these, they are either tunables or they are beyond our control. Our system was only adding 100 millisecond delay on top of this. The consumer bandwidth that we were able to support was 70 Gbps in this experiment. We have some other experiments as well that you can refer in the paper. Experiment 1B to 1D, which test different system stability in different scenarios. In the second experiment, we turned up 120-way message stream, same as before, but this time we doubled the write rate. We have 480 Mbps write rate, 15 destination cluster. This time we allowed the cache layer to scale horizontally, and this time the consumers were reading 10x the messages, so 80 Mbps per consumers. And this is the result that we have. We scaled up the consumers from 1,000 to 20,000 in one of the leaf cluster, and the consumer bandwidth reached 1.8 Tbps. As you can see on the graphs on the right, during the scale up, both data and metadata cache also scaled up, and there was a hash modulo change, so there was temporary unavailability. During those movements, there was fallback to Colossus observed, and aligning with that, the delivery delay also went up. But eventually, when the system stabilized, the delivery delay also stabilized, and we also have other experiments like testing sudden scale up from 0 to 6500, or turning down producer and then turning them back up after 15 minutes, which creates a huge backlog of messages to be delivered. In all those cases, the system does destabilize for a few minutes and then eventually stabilize. We also conducted an ablation study where we removed the cache layer and we were purely relying on Colossus. And we observed that Colossus was running into a lot of unavailable errors, mostly caused due to network congestions. We have added about 25,000 lines of code to develop this system, and there have been several sources of delays. For example, whenever there used to be job rollouts, we have to come up with different strategies to handle the issues. We often run into machine issues because we run our jobs on shared machines, and we rely on system level metrics for rescheduling our jobs in those cases. Intercontinental network delays have been very hard to handle, and they have led to several SLO misses. And this is the numbers from production. This is the numbers that we observed on a day back in 2024. Our P99 is 730 milliseconds, and our consumer cache byte availability has been 99.9%, and we offer SLOs on these numbers. Yeah, and then I'll open up to questions.